Hello everyone. This video is about verification of sampling theorem. Okay. So this is one of your lab programs in PCS lab. Okay. And let us see what is it. Okay. So we will not go the linear way. What we'll do, let us see the program here. Okay. So uh, I hope you can see the screen here. Basically, there are three frequencies here. Can you see there are three sinusoids? Sinusoid 1 plus sinusoid 2 plus sinusoid 3. Okay. So as per the template A cos 2 pi ft, you can see here there is 2 pi, this 100. So this first sinusoid is having a frequency of 100. The second sinusoid is having a frequency of 150. And the third sinusoid is having a frequency of 175. Okay. So as for the template, so how I have defined this particular signal. So this particular signal, 4 is the amplitude. Cos 2 pi ft. In place of t, I have written n here. So n is this discrete intervals of time for which the entire sinusoid is uh, um, represented. Okay. How have I taken this n? So I had taken this n in uniform spacings where my spacing is also called as the time period. It is the space between two consecutive samples. It is, I will start from 0, go till 1000 samples. So here I have decided to take 1000 samples in a second. So my sampling frequency here is 1000. If my in 1 second, if at all I take 1000 samples, the distance between two consecutive samples will be 1 divided by fs. Okay, so that will be my time period. So fs is my sampling frequency and 1 by fs is my sampling period. Okay. So here I will evaluate, and so I have taken as an example sum of three sinusoids. Okay. Hmm. Then let me define my x-axis. For some reason, my x-axis starts from minus fs by 2, which is from minus 500, right, in spacings of 1, and I will go till plus 499. Okay, so I am not starting from 0 to some positive value. Instead, minus 500 fs by 2 to plus fs by 2 minus 1. Then the next line is it takes the Fourier transform. Okay. And I have just plotted the Fourier transform. Now, Fourier transform can be real, it can be a complex quantity also. Just to plot the magnitude of it, see, you can see here I have typed ABS, which indicates absolute value. And for some reason, I have taken a rearrangement function called as fftshift. Okay. So let us see this anyway. Okay. First, let us have a look what is happening here. Okay. So before that, let me brief you. Okay. I will just run this particular first code here and let me check. Yes. So evaluate selection. Now I think you cannot see the screen. Wait 1 second. Yes. Okay, sure. Okay. Now I hope you can see the screen. So I hope now you have got what does a Fourier transform do? Okay. So here you can see you took the Fourier transform and it is containing Fourier transform indicates the frequencies components in the signal. So here you have 0 from this is the frequencies on the positive side, this is the frequencies on the negative side. Okay, so a sinusoid at 100, a sinusoid at 150, and a sinusoid, right? So each of the sinusoids have been replaced by impulses. Okay, each of the sinusoids are replaced by impulses. I would call them as sticks for the time being, as you may not be having an idea of what an impulse is. Just sticks here. This x-axis, by the way, is now frequency. This y-axis is the strength of the signal. Since my signal X had only three frequency components, this plot of Fourier transform has given me three values on the positive side and again three values on the negative side. So I would say a curious student should go through the NPTEL videos about the prerequisites, that is some basics on the Fourier transform. Okay. Now let us discuss why did I choose fftshift. If at all I had not used the function fftshift in MATLAB, I would have started from zero and I would have gone till fs, that is 1000. But I wanted the textbook way. Okay, so in textbook usually Fourier transform is periodic with period 2 pi, and it starts from minus pi to plus pi. Usually minus pi maps to fs by 2 and pi maps to minus pi maps to minus fs by 2, pi maps to fs by 2. Since there are 1000 samples, so from minus 500 to plus 499. Okay. So that's one thing. So a utility of a Fourier transform can be seen here. How cool is a Fourier transform, the FFT tool? Okay. So I can straight away see the frequency components of the signal. Okay. So everything went well. Okay. So that was the thing. So now let us come back to what is sampling theorem. Okay. Now let us come back to what is sampling theorem, the issue at hand. Okay. So for that, what we will do, I will go to your Wikipedia page. Okay. So I think now you can see a Wikipedia page. Okay. So what is the sampling theorem? So the idea of sampling is, suppose you happen to have a sinusoid, something. Suppose you have a signal which is having all the frequencies, say from 0 to some frequency B. Okay. Maximum signal frequency, say, is B. Okay. So I usually call it in my classroom, regular classroom, as FM, the maximum signal frequency. And if at all I want to convert the signal from continuous time to discrete time by taking samples, and to be able to reconstruct, my sampling frequency should be twice the maximum signal frequency. Okay, that's the condition. Okay, so the sampling frequency should be twice the maximum signal frequency. So fs should be greater than maximum signal frequency. Okay, so in our case, in okay, what we saw, so you might have seen we had three sinusoids, right? We had three sinusoids. The first sinusoid was of 100 hertz, the second sinusoid of 150, third one was 175. So my maximum signal frequency in this was 175, and as per sampling theorem, I should take some number greater than 175 into 2. Okay, should be greater than 350. Okay, so the number 350, which is on the boundary, is actually called as Nyquist rate. Twice the maximum signal frequency is called as Nyquist rate, and the sampling at Nyquist rate is called as Nyquist rate sampling. Anyway, the one which we took now as the sampling frequency of 1000, since 1000 is, far above the required sampling, twice the maximum signal frequency, it is called as, situation is called as oversampling. It's called as oversampling. Okay. So now let us talk what's going to happen at Nyquist rate. Okay. So here I have taken the Nyquist rate. So maximum signal frequency of 175. I have taken a Nyquist rate as my sampling frequency, that is twice the maximum signal frequency. Now let me run this image, this piece of code also. And here, now let us see, my output has popped up. Okay. So now let me share with you the other image. Yeah. Okay. So you can see here in this particular image. Now did you see here? I have started from, since 350 samples are there, I have chosen to begin from minus 175 on the extreme left side and up to 174 on the right side, which is my minus pi to plus pi. And since this is the border, okay, so something strange has happened here. So you can see the frequency 100, we can see the frequency 150, and the value at 175, since 175 is missing here in this graph, Okay, I can see a value at minus 175 anyway. Okay, and something strange also. Let me remove this. I want you to see through. Okay, my first sinusoid has an amplitude of 4, second sinusoid has an amplitude of 4, and the third sinusoid has an amplitude of 6. So you can see the Fourier transform not only gives you the frequency content, but it also indicates the strength of the signal. So you can see the first signal is having a strength of 2000, second one is having a strength of 2000, third one is having a strength of 3000. So the ratio, right, it's 2, 2, and 3 is similar to 4, 4, and 6. Okay. Nyquist rate is a border. It's on the boundary. And you can see something strange happened here. So here strength was 700 and here also it was 700. So compared to that, this number should have been something like 1150. Okay. But instead this number has gone to 2100 because something strange has happened there. Okay. Anyway, now let us see what can possibly go wrong. Okay. Again, you can see here, as anticipated, the frequency is 100, frequency at 150, and 175 is missing for some reason. Let's not bother. Now let us see the other case. Now what I will do, again, let me go back to the program and let me run the third case. Okay. So the second sampling, whatever you did just now, we just satisfied the Nyquist rate. It's called as Nyquist rate sampling. The third case, what we have now, you can see here, I have taken sampling frequency of 220, which is clearly less than 175. Okay, but anyway, it is again, if at all I wanted to sample the sinusoid of 150 hertz and to be able to recover the original signal, for 150, at least I should have taken sampling frequency of 300. So probably for 100, this is fine. But for these two frequencies, the frequency is not sufficient. Anyway, let me run this piece also. And let me just show you what's going to happen. Okay. So now the image has popped up and here we go. Okay. So in this particular case, okay, something strange has happened. Okay. So you can see here we have the frequency of 100. Strengths are also fine. 4 is to 4 is to 6 strengths are also fine. But you can see, did you see this thing? This Fourier transform is indicating that there is a frequency of 70. There is a frequency of 70, which is not there in the sinusoid. And there is a frequency of 45, which is strange, okay, because this frequency is not part of my original signal. I somehow, for some lack of knowledge and judgment, have taken a frequency less than Nyquist rate, and I have ended up generating two strange frequencies which are not part of my original signal. Okay, so this particular situation is called as aliasing. Okay, this is called as aliasing, right? You might have heard this use of word aliasing in popular culture, right? So it's somebody taking in somebody else's name. Okay, that's called as aliasing. And here also, the signals, whatever it is, there they have been translated, right? The signal components translated to some other frequency, which completely made the entire signal useless. So three types of sampling. Nyquist rate sampling is when you sample a signal at twice the maximum signal frequency, which just satisfied at border. We are happy that no strange frequencies are there. Oversampling is when you sample at a much higher rate compared to your Nyquist rate. But you might have realized here, see, to store these, you need 1000 space memory units, right? So oversampling is cool. It gives you a nice frequencies and all. Recovery is cool, but then it takes more time because you need to transfer, communicate 1000 samples. You want to store them. You need to store 1000 samples. That takes much more memory. Nyquist rate is somewhat optimum, right? That's the boundary, right? It needs optimum number of memory locations and optimum amount of time to transfer. Undersampling needs less memory. Undersampling needs, you can transmit faster, but then aliasing is the problem, which renders the entire signal useless. Okay, so that was about sampling theorem. What we just saw was the sampling theorem in the frequency domain, and we have learned two terminologies. The first terminology is Nyquist rate, which is twice the maximum signal frequency, and the second terminology is aliasing, which is the condition that occurs when you take sampling frequency less than Nyquist rate. Okay. And now what do I want you guys to do? So what I want you to do is I have written here, observe the alias frequencies appearing in case of undersampling. Then I want you to try, okay, let me try it here itself, okay, so that you can also. So what is it, by the way? Instead of sum of sinusoids, right, I will do the product of two sinusoids. Now, only for the first case, okay, just for fun, let us observe this, okay. So you can see here, I will take instead of plus, I will multiply the dot multiply. Dot multiply. Do you know what is a dot multiply? What is the difference between multiply and a dot multiply? So can you see here, if at all I show you, wait, let me just show you. I have two samples here. Okay, wait. Let me run this piece for the timing. Let me run this. Okay. I hope, okay. I want you to observe this particular workspace here. Now you see the signal X, by the way, here is 1000 samples. So this particular first sinusoid is also had 1 cross 1000. Second sinusoid also 1 cross 1000. So when I want to multiply in an array, first element with first element, second element with second, and so on, it's called a scalar multiplication, element by element multiplication, which is when I need to use dot multiply. If at all I want to multiply 1 cross 4 with a 4 cross 1, that's a vector multiplication. Okay. I want to do a scalar multiplication here. Anyway, I have executed this particular thing. Now let me just show you what has happened. So everybody think for some 20 seconds or so. Now can you guess if we choose enough frequency, or what is the maximum frequency component in this particular signal? Any idea? You can see first signal is of 100, second signal is of 150 hertz. Okay. So when you multiply two sinusoids, cos A cos B equal to half cos A plus B, A minus B, right? I don't know cosine, but the frequency component is A plus B, A minus B. Okay. So this particular signal, sum of two sinus, product of two sinusoids, results in two frequencies. So this particular signal here contains, now let me take you to the graph. Here, there you go. So you can see here 150 and 100, right? So there are two frequencies here. Cos A plus B, have A plus B and A minus B. So the first one here you can see is 100 plus 150. It's a 250 A plus B. Second one is A minus B. 150 minus 100 or 100 minus 150. Cos of minus theta is also cos theta. So that should not be an issue. So for this particular case, you can see we got frequencies 50 and 250. Okay. So, this is what we have been by hearting since our PUC days, right? So that's it. So that was sampling theorem in frequency domain. Now what we'll do, let us quickly try sampling theorem in uh, time domain. Okay. So now let us see sampling theorem in time domain. For that, once again, let me take you to this MATLAB interface. Okay. So sampling in time. So time domain is easier for us to understand. So in this time domain, I have simply taken a signal of 10 hertz, and for a soothing visualization, I have taken my sampling frequency. 20 should have been sufficient, okay, but I have chosen 100 for an oversampling. Okay. See here, the choice of frequency suddenly has changed because in time domain, I want it to be to be able to, we need to visualize this on the screen, right? That's why I chosen a very less frequency. Then I will try it with 20 hertz also, which is my Nyquist rate. And then I will try this with some number which is less than 20. So I've taken 14. Okay. So what is the difference, by the way? If at all it is only the time domain, so I will simply plot. Okay. So I think this is not needed. The for frequency domain is also there. But if at all I plot only X here, first 100 samples, if at all I only plot X, that would give me the time domain. If at all I plot xk, which is the Fourier transform of x using the function fft, then it will be the frequency domain. Okay, now let me control A, will run the thing. Okay, and now let me show you the graph, what has happened. Okay, so here you can see. So when I chose my sampling frequency as 100, you can see the similar looking sinusoid has popped up. I have used the function plot here to give a illusion of a continuous signal, even though the signal is discrete. Okay, you can see here there are so many samples. Sample here and sample here. Wait a second, can I make it better? Okay, okay. Sample here, sample here, sample here. So many samples are there. For every cycle, now there are 10 samples. And that what constitute, you can see a point here, you can see a point here, you can see a point here, and so and so. So this is oversampled. And in Nyquist, you can see there are only two samples, one at the top, one at the bottom. But then you still get a feeling of same number of cycles, right? You can see in 1 second there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cycles as anticipated. But when I took sampling frequency of 14, you can see here there is only one cycle, two cycle, three, and a 3.5, strangely. So we lost our signal there. Okay, and it is giving an impression as if the sampling frequency signal doesn't contain a 10 hertz sinusoid at all. Okay, so that was visualization of sampling frequency in time domain. But I am somehow, I am a big fan of Fourier transform, and I also want you to appreciate Fourier transform as a very powerful tool to analyze frequency components of a signal. So that is my video. You try different sinusoids with different strengths, right? Change their amplitudes, change the frequencies. You add, you multiply, you add some DC also. Okay. So what's with the DC? Okay. So wait, let me just show you. Okay. So everybody knows what is this DC. Now see here, I have two sinusoids. Let me again revert back to sum of sinusoids, and again along with this let me keep a DC here. So what I will do for this particular sinusoid, I will simply add number. Okay, so I will add just a plus of 5 here, okay, or a plus 8 here. Now adding this plus 8 here, it simply indicates a bias of 8. Okay, and let me just take the, before that I should delete this image. Okay, now let me run this and let me take you to the image that has popped up. And here you can see in this particular case, you got sinusoid at 100, sinusoid at 150, sinusoid at 175. Then you have a value at 0 because we added an 8, which is a bias. Bias is a DC bias. And what's the frequency of DC? It's a 0. Okay. So that was sampling theorem. I will paste the program in the comment section. Okay. Give it a try before coming to next lab. Save the figures. So how to save the figures, by the way? You can go to extreme top left corner, file, save as, default folder, my documents, MATLAB, or whichever the folder it is. Give it a proper name. Okay. And save it as .fig or .jpg. Okay. .jpg is a dumb image, whereas if at all you save it as .fig, you can later open it in MATLAB and do any convenient editing in it. Okay, whereas JPG is the end of story there. Okay, whatever you observed that day will be the image. Okay, so try this on your own and let me assess you in the next lab when you show me your laptop screen what you have done. Okay, so that's it. Thank you.